Hello again and welcome to our final mini lecture for Unit 8, and in this case we're going to talk about the death throes of high mass stars. So in the last mini lecture we covered the evolution of a Sun-like star, and we saw that the Sun-like star does different nuclear fusion. It can begin fusing helium into carbon and oxygen, but that's all the further it can go. Gravity's not strong enough to squeeze the carbon and oxygen enough to get it to do any type of fusion. But we will find that when we go to stars more than 8 times the mass of the Sun, the fusion processes are different, and this results in a drastically different end state for the star. Up until the second red giant phase of the star, the life cycle of massive stars is very similar to the life cycle of the Sun. Happens much faster. Remember, we learned that massive stars have much shorter lifetimes than the Sun, but the steps are basically the same. The star begins on the main sequence and it is fusing hydrogen into helium, so hydrogen fusion into helium, until it runs out of hydrogen in its core. The helium does not begin nuclear fusion right away, so we have a core of helium ash. The star swells into a red giant until gravity can contract the core enough to begin helium fusion, and the helium fuses into carbon and oxygen. The star begins to shrink and get hotter again, and now it's doing helium fusion into carbon and oxygen in the core. It's doing hydrogen fusion in a shell outside of that, and it continues this way until it uses up all of its helium in the core, and again it will swell into a red giant as we have a core of carbon and oxygen ash surrounded by a shell of helium fusion, which is itself surrounded by a shell of hydrogen fusion, and then further out the rest of the star is too cool for any fusion, so we still have a lot of hydrogen left. Up to this point, both the Sun and these very massive stars have a very similar life cycle. However, when you get to about 8 times the mass of the Sun, now gravity can squeeze the core enough that before we get to this degeneracy, the temperature gets high enough to allow carbon to begin to fuse. Now, carbon can fuse by several routes. I don't expect you to memorize these, but I put them up here to show you some of the things that can happen. 2 carbon atoms can fuse together and produce magnesium, and in the same thing release energy. Or 2 carbon atoms can fuse together, produce oxygen, and release some helium particles, which then can go out and do more fusion. Or we can make sodium, or we can make neon, several options for what can happen when 2 carbon atoms fuse. All of these will happen to some extent in the core of the massive Sun. So carbon fuses into oxygen, neon, and magnesium in the core of these massive stars, and then we now have a lump of oxygen, neon, and magnesium ash surrounded by a layer that's doing carbon fusion, surrounded by a shell that's doing helium fusion, surrounded by a shell that's doing hydrogen fusion, and then the outer layers of the star that aren't doing anything. Now gravity can then begin to squeeze this oxygen, neon, magnesium down until fusion of it can begin. And for example, oxygen can fuse to make more magnesium, it can fuse to make silicon, it can fuse to make phosphorus, it can fuse to make sulfur. Again, several different things can happen. Meanwhile, neon and magnesium are doing their own fusion, but basically we're making elements up near silicon and sulfur in the periodic table. And again, this releases energy, so the star can power itself until it uses up all the oxygen in its core, and now it has a lump of silicon at the core of the star, surrounded by a layer that's doing oxygen fusion, surrounded by a layer that's doing carbon fusion, surrounded by a layer that's doing helium fusion, surrounded by a layer that's doing hydrogen fusion, and then the outer layers of the stars that are too cool to do anything. These stars will have enough gravity to squeeze this silicon core so that it can begin fusion into nickel and iron. And so silicon combines to make nickel in the core of the star. That releases energy. That can power the star. And this will run until we run out of silicon. So now we have a star that has iron and nickel at its core that can't do any fusion. surrounded by a layer that's doing silicon fusion into iron and nickel, surrounded by a layer that's doing oxygen fusion into silicon, surrounded by a layer that's doing carbon fusion into oxygen, surrounded by a layer that's doing helium fusion into carbon, surrounded by a layer that's doing hydrogen fusion into helium, surrounded by the outer layers of the star that are too cool to do any fusion whatsoever. Basically, what you do need to know is that we have a resulting star that looks kind of like an onion. Hydrogen on the outside that's too cool to do any fusion. Most of the fusion happens down deep inside the red giant, where we have several different layers of different types of fusion, and at the very center of the star we have iron and nickel. Another thing to know is that each of these types of fusion occurs on a faster and faster time scale, because first of all, the fusion doesn't release as much energy as previous types of fusion. Second, the star is getting brighter in this red giant phase, so it needs to release even more energy. And because we keep mashing atoms together, we have fewer and fewer atoms to go around to do fusion. So the result is that the time scales get really short. So for a very massive star, 125 times the mass of the Sun, it may be able to do hydrogen fusion for 7 million years. But the helium fusion will just be 500,000 years, much shorter. The carbon fusion, just a few hundred years. And the oxygen and silicon fusion, we're talking about days. I mean, here in astronomy, when we're used to talking about timescales of millions or billions or trillions of years, now we're talking about one entire episode of the star's life cycle that lasts for one day, and that's fusing silicon into iron. In the meantime, the outer parts of the star keep swelling, and in these massive stars there's so much energy coming out of the core, and the outer layers get so fluffy that the outer part of the star becomes unstable. This is a picture, it's not an artist rendering, this is a picture taken by the Hubble Space Telescope of a star called Eta Carina. Eta Carina is about 100 times the mass of the Sun, and it's a moderately faint star these days. You have to be in the southern hemisphere to see it, and if you were to look at it, you wouldn't think there's anything special about it. But in the mid-1800s, this star brightened up to become temporarily the brightest star in the sky besides the Sun. And then it slowly faded away, and when we look now, we see the remains of this as these two big lobes on either side of the star. The star here is kind of overexposed in the center, so you don't see it. These lobes are each about 5 to 10 times the mass of the Sun, and back in the 1850s the star had a massive eruption on its surface where 10 times the mass of the Sun came out in this big eruption, and that's why the thing got so bright. But the star's still there. It didn't explode. It's just like pushing off material. And you can see further out remains of previous eruptions that probably happened before people tens of thousands of years ago, before any people were around to record it. And so this is a massive star. It's highly unstable. The center is doing some sort of fusion. The outer part is erupting off massive amounts of material. Obviously something drastic is going to happen. So these massive stars are rushing headlong toward the abyss. Up until now, stars have been doing fusion because fusion releases energy. The star needs the energy because this energy is in the form of a high temperature of the center of the star that allows the star to have gas pressure that keeps gravity from collapsing the star downward. Remember, pressure is supporting the star against gravity. The pressure needs high temperatures for this to happen. The high temperatures require a constant source of energy, or else the star would cool off. As you go from hydrogen to helium, you get energy. This graph shows basically how much energy you get out from a fusion reaction. Hydrogen to helium gets you a lot of energy. Helium to carbon releases more energy. Carbon to oxygen releases more energy. But by the time you get to iron, you're sort of at the bottom. If you fuse iron into something heavier, you don't get energy out. You instead require energy. Fusing iron absorbs energy. So when a massive star tries to begin iron fusion, it suddenly begins losing energy instead of gaining energy. And this is not a stable situation, because if you lose energy, that means your temperature goes down, which means that gravity is going to squeeze it. Gravity will heat it back up, but that just gives you more energy to do more iron fusion that then gets absorbed. And you have a runaway reaction where basically the center of the star, by doing fusion, becomes cold. Because of this, there's not any gas pressure to support the star against gravity. So gravity begins squeezing the star very rapidly. It's almost a collapse. In our lecture on sun-like stars, we saw that gravity ends up being stopped at the end by degeneracy pressure, by not being able to put two electrons in the same place at the same time. However, in a very massive star, even this degeneracy pressure is not enough to stop gravity. And basically, gravity squeezes the electrons to the point where the electrons merge with protons, and this makes neutrons. Remember when we talked about atoms that atoms are mostly space. We had this apple seed sized nucleus inside a football field sized atom. Now the electrons go away, and so suddenly the entire atom is the size of that apple seed. All this space opens up and gravity can squeeze down the star really small. 1.5 times the mass of the sun gets squeezed into something that's only a few miles across. It's a giant atomic nucleus made out of a sun's worth of neutrons. So the center of the star very quickly collapses downward from being relatively large to something a few miles across. For the outer parts of the star, this is like Wile E. Coyote running off the edge of the cliff. There's no layer underneath the outer parts of the star to hold it up against gravity, and it begins to collapse downward. This inward collapse heats stuff up very quickly. It sets off a chain of uncontrolled nuclear reactions that releases a tremendous amount of energy, and this causes the outer layers of the star to explode back outwards, and we call this explosion a supernova, and the star rips itself apart in an explosion. In our next unit, we will talk more about supernovae and more about the results of this supernova explosion. But for now, the thing to remember is that the massive stars can do nuclear fusion up until we get to iron. Once they've made iron in their core, the star can no longer make energy by nuclear fusion. Gravity wins and squeezes the core until the electrons and protons merge and make a giant atomic nucleus that's about 10 miles across and made out of neutrons. The rest of the star collapses inward, begins to collapse inward, and then explodes outward in a supernova. Know that much, and you're doing really well. So low mass stars like the Sun die gently in a planetary nebula and make a white dwarf. High mass stars die in a tremendous explosion called a supernova. So now I've told you these nice stories about these two stars. How do we know it's right? Stars live for millions or billions of years, which is much longer than the lifetime of any astronomer sitting and watching. So we can't sit and look and see if stars actually do this. We need a better way of understanding if our theories are right. First, let me show you the theory of what a star looks like. It's these terrible math equations. There are 4 math equations here. I do not expect you to even begin to understand them, but I wanted to show them to you to let you know, yes, there are math equations. We can plug these into a computer. We can solve them. The first one tells us about pressure. The second one tells us about density. The third one tells us about temperature. And the fourth one tells us about nuclear fusion. Combine all those in a computer and you can predict what a star should look like. But again, how do we know this is right? Well, we have some predictions. One prediction that these hypotheses, these theories make, is that massive stars should end their lives first. Our second prediction is that low mass stars like the Sun, they should be on the main sequence for a long time, then they become red giants, then they shrink into these horizontal branch stars, then they grow into red giants again, then they make a planetary nebula, then they become a white dwarf, and the white dwarf should cool and fade. So how can we tell? Well, if we have a group of stars that have a bunch of different masses, because different masses all live out their lives at different speeds, yet all the stars are the same age, we can test and see, do our stars the computers spit out look like the stars in the sky, and can we see each stage of this process? Thankfully, we do have groups of stars that have different masses, but yet all the stars are the same age and made out of the same material. These are the star clusters we talked about back in Minilecture 2. Let's look at a globular star cluster. Globular star clusters are old enough, they're 10 to 13 billion years old, so they're old enough that sun-like stars are ending their lives, and they have hundreds of thousands or even millions of stars, so we should be able to see all stages of the life cycle. So on the left is a picture of a globular cluster taken from the ground. On the right is the center of the globular cluster looking with the Hubble telescope, and you can see we've got faint stars, we've got bright stars, we've got red stars, we've got blue stars, we've got a whole bunch of stars here. Does what we see in this Hubble telescope picture match our predictions? Here is a Hertzsprung-Russell diagram made from Hubble Space Telescope data of a globular cluster. You can see the main sequence. You can see the stars that are up into red giants. You can see this thing called the horizontal branch. You can even see the stars that are in their second red giant phase in a planetary nebula. And you can even see a lot of white dwarfs, including some hotter bright ones and some fainter cool ones. This is exactly what we had predicted with our models of stars, with folding in all the physics, everything we know. That whole story I told you predicts this exact shape for globular clusters. This is confirmation of our hypothesis that we understand what stars are doing, and that stars change and grow into red giants, become white dwarfs. We can see that in globular clusters and test all this. Our understanding of the life cycle of stars, it's a complex process. It involves some complex physics. There are lots of parts to it, lots of vocabulary here for you to learn. But I want you to understand we have been able to test this using not just globular star clusters, but also open star clusters for more massive stars. And we can see that our predictions do hold true. So this ends our study of the life cycles of stars. In our next unit, we'll go on to stellar death and life after death, or zombie stars, and then we'll move on out into the universe.